Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wondered why sometimes different scientists looking at the same problem end up with totally different answers, even when they think they're doing everything right? Well, today we're diving into a really cool idea that tackles this head-on. Imagine this: you've got a puzzle, and you're not quite sure how to put the pieces together. You try one way and it looks one way, you try another and it looks completely different. That's kind of what we're exploring today, the idea of analytical flexibility. It's a fancy way of saying that when scientists look at data, there are often many different paths they can take to reach a conclusion, and these different paths can lead to different answers. This can be a problem because it can make it hard to trust research, and it's something we desperately need to understand better. So, how do we actually learn about something as tricky as analytical flexibility? The researchers in this paper had a brilliant idea. They decided to use something called a registered report and a many analysts approach to teach undergraduate students about it. Think of a traditional research paper like a finished meal. You see the result, but you don't see all the chopping, dicing, and maybe even a few burned bits on the side that went into making it. A registered report, on the other hand, is like getting a recipe before you start cooking, with a promise to publish the final dish no matter how it turns out, as long as you follow the recipe. Basically, analytical flexibility means that for any given question and any given set of data, there isn't just one single right way to analyze it. You might clean the data a little differently, decide which participants to include or exclude in a particular way, or use slightly different statistical tests. Each of these choices is often perfectly reasonable. However, when researchers have to choose between several reasonable options, they might unconsciously or consciously pick the one that leads to the most interesting or supportive findings. This is where problems can creep in, and it's a big part of what the replication crisis in science is all about. We want more transparency. The American Psychological Association, which shapes psychology education, is really pushing for students to learn about open science and transparency. This is super important because it's about building trust in the research we rely on. So, how can we teach students about these new, more transparent ways of doing science? The paper argues that analytical flexibility is just a natural part of doing research. Experts can disagree on the best way to analyze something, but this very flexibility can open the door to what's called p-hacking. P-hacking is when you keep trying different analyses until you find something statistically significant, that is, something that's unlikely to be due to random chance. Imagine you're rolling dice and you want to get a 6. If you only count your rolls when you get a 6 and ignore all the other numbers, you might start to think 6s are way more common than they really are. P-hacking does something similar with data. It can make a result seem more important or real than it is because you've cherry-picked the analysis that looked good. To really see this flexibility in action, the researchers looked at a research project called Many Analysts. In this kind of study, they give the same data and the same research questions to a bunch of different people, and then they see how their different analytical choices lead to different results. It's like having a whole team of chefs try to cook the exact same dish with the exact same ingredients, but each uses their own unique techniques. The outcomes can be surprisingly varied. So how do they use this in a classroom? They use registered reports. These are super cool because the researchers submit their study plan, including their hypotheses and how they'll analyze the data, to a journal before they even collect the data. The journal then says, okay, this plan sounds good, and we promise to publish your results, whatever they are. As long as you stick to the plan, this whole process reduces the temptation for p-hacking and harking that's, hypothesizing after results are known, or making up a hypothesis after you see the data. The activity described in the paper works like this. Students get to read the stage 1 registered report, which lays out exactly what the researchers plan to do. Then, they get the actual data. Their job is to follow the analysis plan as closely as possible. After they've done their analyses, they come up with their own results. The key here is that students aren't expected to all get the exact same numbers as the original researchers. Instead, they compare their results with each other and, most importantly, with the final published Stage 2 registered report. This comparison highlights where and how analytical choices can lead to different outcomes. For this to work, the instructor needs to pick a good registered report. It should be on a topic that's interesting to students, and the statistical analysis should be something they can actually do with their current skills. They also need to make sure the data is accessible and well documented, which is called open data. A data dictionary is like a cheat sheet that tells students what each piece of data means. In their example, the researchers had 7 undergraduate assistants, who they called analysts, work on a registered report that looked at virtual embodiment, stereotype threat, and awareness of racism. These students helped collect the data, so they were already familiar with the study. They read the Stage 1 manuscript, got the data, and then they each implemented the analysis plan. creating their own R scripts to analyze the data, essentially trying to reproduce the original study as planned analyses as best they could. The results were fascinating. Even though the students were trying to follow the same plan, they ended up with variations in how they scored the data, how they handled missing information, and even how they checked if the data met the assumptions for certain statistical tests. These small differences in how they handled the data led to different sample sizes, and for some hypotheses, different conclusions. For example, when testing hypothesis 1A, 1B, and 1C, different analysts arrived at different conclusions. For some hypotheses, they all agreed there wasn't much going on. But for others, like hypothesis 1B, some analysts found interesting results, while others did not. This clearly shows that analytical flexibility can indeed lead to different conclusions from the same dataset. One really interesting takeaway was the students' reaction to not finding strong support for the hypotheses. Many of them were confused or worried they had done something wrong because they weren't getting significant results. This highlights a common bias in science and in how we're often taught statistics, a preference for positive, statistically significant findings. The students' initial survey showed they expected most of the hypotheses to be supported, making the null results even more surprising and concerning for them. Overall, this exercise beautifully demonstrated that even with a pre-registered plan, there is still room for analytical flexibility. It also showed that when plans aren't super specific, like the section on checking statistical assumptions, which was quite vague, it leads to more varied approaches among analysts. This is incredibly valuable for students because it makes them realize that research isn't always a straightforward path, and that the way we analyze data really matters. So, what does this all mean for us? Well, this study shows that teaching students about open science practices like registered reports and using a many analyst approach is a really effective way to teach them about analytical flexibility. Students get hands-on experience with real data and learn to think critically about how research is done. They see the strengths of these open science methods in making research more transparent, but also how they can still have limitations. The discomfort with null results is a big deal. It tells us that even early in their careers, students are picking up on the implicit pressure to find significant findings. This is a perfect opportunity for instructors to dive deeper into why null results are just as important, if not more so, than positive ones and how publication bias can distort our understanding of science. Imagine if we only ever heard about the lottery winners and never about the millions who didn't win. Science would be pretty misleading. For those of you interested in diving deeper or for instructors looking for materials, the paper points to great resources like a Zotero library of registered reports, many of which have open data and available stage 1 manuscripts. This is a treasure trove for anyone wanting to explore research more transparently. The authors also suggest other ways to get at this idea, like using study registrations or even using large language models or LLMs to explore different analytical possibilities. For example, you could ask an LLM, how many different ways could you analyze this particular part of the data? And then have students evaluate those suggestions. This is a really forward-thinking approach to integrating new technologies into scientific education. Ultimately, this paper makes a strong case for why teaching these open science principles, especially analytical flexibility, is crucial for undergraduate psychology students to become critical consumers and producers of research. It's not just about knowing statistics, it's about understanding the entire research process and the many decisions that shape our scientific knowledge. From my perspective, this is a fantastic way to teach statistics and research methods. By letting students grapple with real data and see how different analytical choices can lead to different paths, they develop a much more nuanced understanding of science. It moves beyond simply plugging numbers into formulas and gets them thinking critically about the underlying assumptions, limitations, and the very real human element in scientific inquiry. The fact that the students felt discomfort with null results is a vital teaching moment, highlighting the importance of valuing all research findings, not just the ones that confirm our initial hopes. This pedagogical approach not only teaches valuable skills, but also fosters a more robust and honest approach to scientific discovery. What do you all think? Have you ever encountered a situation where you realized there were multiple ways to look at the same problem and it changed your conclusion? Let us know in the comments below. If you found this breakdown helpful and want more insights into the fascinating world of psychology, make sure to hit that like button, subscribe to RUBIN'S Mind Lab, and ring that notification bell so you don't miss our next exploration. Until next time, stay curious.